Okay, welcome back everyone for our second session of the day. So, the story about this upcoming talk is about 2 p.m. yesterday. I was here helping the volunteers get some stuff ready, and I was off at the UQ Union building to go get lunch. And I was chatting over IRC with one of my colleagues back in Canberra where I work, saying, yeah, everything's going good at CompCon. And Daniel here replied with, I've got nothing better to do with my weekend, you know. I mean, I could totally come give a talk at CompCon. And I'm like, funny you say that, because we happen to have a vacant speaker slot at about 10:30 tomorrow morning. So about 2 hours later, a talk abstract was written, and an obscene amount of money was handed over to Qantas to boost some executive bonus by a few dollars. And about 8 o'clock this morning, he flew into Brisbane to give this talk. So this has been prepared in about a 18-hour turnaround.
It's a quality talk.
It's a quality talk, he assures me. And I can assure you, Daniel is a very smart guy, so when he says it's a quality talk, I think it's a quality talk. Anyway, Daniel Axtens is a graduate software engineer and kernel developer at the IBM Linux Technology Center in Canberra. He has worked on a number of Linux kernel-related and open source projects, which he is about to talk to you about in his talk, Being a Kernel Hacker. Please welcome Daniel.
Thanks, Andrew. So, yes, I'm talking about being a kernel hacker, and I want to talk about that in sort of two aspects. I want to look at what it's like technically, but I also want to talk about how I got there and the sort of career aspects to it in the hopes that one day some of you will want to be kernel developers as well. So, having said that, this is not a recruiting talk. So who am I? Andrew has covered most of it. My name is Daniel Axtens. You can email me. You can also follow me on Twitter if you want my stream of amusing retweets. And as Andrew said, I work for IBM in their Linux Technology Center. So IBM builds a bunch of servers and other things, and we want Linux to run on it. And in order for Linux to run on it, people need to do the development work for that. So I am a kernel hacker. I develop code that goes in the Linux kernel, and in what I think is probably my crowning achievement of 2015, you can now Google or look up on GitHub the Linux kernel and actually find code by me in it, which is awesome. And one of the really big perks of working in a kernel as a kernel developer is that you end up with code running on the devices that everyone uses every day. So, I'm also a recent grad. I graduated from ANU at the end of last year. I actually did engineering, so mostly electronics-y. My thesis project was attaching lasers to hexacopters. You can ask me about that later if you want. And I had an interest in low-level software design, in interfacing software with hardware, and that's sort of how I ended up as a kernel developer. So, kernel hacking. As I said, there are two things I want to cover. What is kernel hacking? What's it like? And how do I become one? To talk about what kernel hacking is, we first need to know what a kernel is. I'm going to assume that most of you are vaguely familiar with the concept, but just to sort of reiterate it, the kernel is mostly the layer that sits between your hardware and the software that you want to run on that hardware. So if you have a program and you want to read a file, you need to talk to the kernel. The kernel needs to go and figure out where on your disk that file sits. It needs to talk to the disk controller and ask for those bits. It needs to get them back. It needs to reassemble them. It needs to check no errors occurred. If errors occurred, they need to be propagated back up to you. So you use the kernel for that. If you want to talk to the network, you need the kernel to talk to your network card, to send a packet, to handle all of the networking stack. If you want to use a keyboard or a mouse or a monitor, you also need your kernel. So basically, your kernel is everywhere, and it's anything you want to do that sort of touches the rest of the world needs to go through your kernel. For those of you with more of a computer sciencey background, the kernel also manages your virtual memory and your multitasking. So switching, if you want to run 10 applications and you've got 2 CPUs, you need to find some way of switching them back and forth and making sure they don't trample on each other. The kernel does that as well. So, Linux is a kernel. People also use Linux to refer to an operating system, and I don't want to go into that. Linux is a kernel. It is probably the premier open source kernel, and it is big. It has, last I checked, 16 million lines of code, and that's not including things like comments, of which we do have some. It has the single most drivers of any operating system. So because vendors traditionally don't develop for Linux, all of the Linux drivers for hardware end up bundled into Linux, rather than, say, on Windows, where Windows supports some drivers, and then you download a driver from your hardware manufacturer's website. Linux is more, everything's in the kernel. So we have hundreds, if not thousands, of device drivers in the kernel. We also support a wide variety of different machines. So, I mean, most of you have laptops or desktops. They'll be running 64-bit x86 chips. Most of you will have smartphones. They will be running, let's go with Android because it runs Linux, some form of ARM chip. If you buy a big server from IBM, it will run either a PowerPC chip, or if you buy a mainframe, an S390 chip. I don't do mainframe development, so I'm a bit fuzzy on that. So there are a number of, and all of those are quite different, right? So this is not a hugely technical talk, so I'm not going to put snippets of C code up, and I'm not going to talk about assembler. But just to give a really short digression, all of those architectures are in fact very different. So on PowerPC, for example, all of your instructions are always 4 bytes. On x86, your instructions just wildly vary in length. And they all have vastly different hardware. They have vastly different pretty well everything. And yet the one kernel code base supports them all. I opened my computer and I ran ls. There are 31 different architectures that the kernel supports. And each of those all come with a bunch of different variations on them. So Linux supports a lot of different things. But the tech specs are actually not really the most interesting part of Linux. I think the most interesting part of Linux, and the thing about tech specs is, right, you can Google this. It's pretty easy. You can even clone the Linux repository and play with it. What I really want to do is give you a flavor of what it's like to be a Linux kernel developer. And I think that's, rather than giving you a tour through the source code, I think that's better served by giving you a brief wander through the development process. And I think the one word I would use to describe the development process is frenetic. Every time the Linux kernel is released, so every time we do 4.2 or 4.3 will come out in a few weeks, 4.1 came out a few months ago, each one of those contains around about 10,000 distinct changes. So we call them commits. So they're basically in theory, one logical change. The Linux kernel had, in each release, about 10,000 of those. They come from hundreds of developers, including me, hundreds of developers across wildly disparate companies. So you have commits from IBM, you have commits from Intel, there are even commits from Microsoft to support their virtualization platform. And all of those companies have completely different aims in life, and most of them want to kill each other. So how do we keep, as the Linux kernel community, how on earth do we keep Linux ticking over? How do we keep, when people try and submit changes, how do we know if they're going to build? How do we know if they're going to build everywhere? How do we know that they're not going to break everything? I think that's probably one of the really interesting things about Linux development. I think there are 3 main things that make Linux tick as a software project. And that's what I'm going to spend some time talking about. The first one is modularity, right? Now, you've probably all done some programming. You've probably all heard, yes, your code should be modular. You should put things that don't interact in different places and keep your code clean. And Linux actually does this, right? If I make a change to the PowerPC architecture, I can be very confident that it's not going to arbitrarily break a file system, or IPv6, or ham radio, which we support in the kernel. There are a lot of things we support in the kernel. Linux gets modularity really, really well. And I think that's probably one of the big things that allows parallel development much more readily than pretty well any other software project I've seen. There's also, no, I'll talk about that later. There are a bunch of very strong, not technical, but social processes that go into building the Linux kernel. So I'm going to talk about two of them. One is the way you get code into Linux, right? So if you have a project on GitHub, or you're doing stuff yourself, or working on several other open source projects, you sort of make some changes and then send them, and someone merges them, and it's usually a reasonably simple and easy process. Linux is not like this. If you want to get a change into the Linux kernel, there are a number of hoops through which you have to jump. So first you have to write your code, right? That's the first step. That's often the hardest step, but it's only the first step. You take that code and you figure out what it relates to. So for me, that's usually the PowerPC architecture, because IBM is one of the two big users of the PowerPC architecture. So then I need to take those code changes, commits in the jargon. I need to turn them into emails that I then send to the email list relevant to that subsystem. So if I'm doing PowerPC development, I send that to the Linux PPC mailing list. If I'm doing SCSI development, which is a system for attaching disks to computers, I have to send it to Linux SCSI. If I'm stupid or unfortunate and do a change that affects 3 or 4 different subsystems, I have to send it to all of them. And so those patches go out to mailing lists. And then the people on those mailing lists get an opportunity to chime in on them, so they can say, you've omitted to do this, you've broken the coding convention here, or that's good, which is sort of what you want. Then the subsystem, so if I submit code to PowerPC, that subsystem is maintained by a guy, and that guy is called Michael Ellerman, and he works in the office with me. He has to look at all of the changes that are submitted to him on the mailing list. He has to decide which ones are worth including and which ones aren't, and then he takes those changes from the mailing list that he thinks are good and applies them to his copy, I guess, of Linux, his branch or tree. The jargon's not really important. He takes those changes. And then, at a particular point in time in the release cycle, which I'll get to, he then sends those changes to Linus Torvalds, who is the guy who, you may recognize the name, he's the guy who runs and wrote Linux. And so, at any point in that process, someone can go, there's a problem that you need to fix, or you've done the least possible work to achieve this, you're being lazy, do it better, or that's just wrong, why on earth would you do that? All of which have happened to me or members of my team. So it's rigorous. There's a lot of code review, not formalized code review like there must be, it's not you send the code to this person's job is to review it, but there is a lot of community-driven review. That's one half. The other half is the release process. So as you know, Linux has versions. We've released version 4.2, and we are maybe 4 weeks away from releasing 4.3. The way this works is not overly simple to explain, but basically there's a separation between features and bug fixes. And there is only a certain window in which you can submit features, and then for the rest of the time, the only code that's accepted into Linux is bug fixes. And that way, there's some sort of order in when things are done and what's accepted when, and an ability to control code quality, I guess. So, I'll give you an example later that will make more sense of that process. Lastly, we have really excellent tooling and systems around the Linux kernel. And this is one of the, I guess, more surprising elements of working in Linux kernel development is we've actually got tools to do all sorts of things. So how do you track changes to your source code? People used to do that with CVS or Subversion. None of them really cut it for Linux. So Linus wrote his own, and it's called Git. It was, at the time, vastly more capable than anything else. It is now there are other tools which arguably are as capable. Git is still very user-unfriendly, but it has all of the market share. So we built a tool in order to let us do what we were trying to do. I had another example. That was, and this is the second diversion into slightly more technical stuff. Linus wrote a C semantic parser called sparse. So basically what it does is it parses C and looks for particular classes of stupid mistakes. Stupid but subtle and easy to make mistakes. In particular, there's a division between kernel memory and user memory, and there's a division between normal memory and memory that represents a device. And you actually need to keep track of all of those and not use user memory when you meant to use kernel memory, or kernel memory when you meant to use user memory. Or if you don't get these right, you end up with a large chunk of security vulnerabilities, and you also end up with things randomly not working. So sparse detects this, and a bunch of other less interesting but still useful code control checks. We've also written, in fact, someone in OzLabs wrote a tool to keep track of the huge volume of posts that end up on a mailing list. That's called Patchwork. So we build a lot of tools just to do things at the enormous scale at which we operate. And the last sort of big system that we have, I've just lost track. There we go. The last big system that we've got is something called Linux Next. So we have just, I think, about 220 different subsystems that people are maintaining, all of which do different things. So there's one for PowerPC, x86. Every different file system will have a subsystem that's maintaining it. There's a concurrency primitive called RCU that's got a subsystem. There are 200 of them. It's a lot to keep track of. And it's easy to make it. If you make a particularly far-reaching change in one, it can conflict with a change in another. And so what happens is every time a maintainer decides that they're going to take a patch, all of the things that they want to put in the next version of Linux, so they're what's called their next trees, all of the things to go into the next version of Linux are picked up by this project called Linux Next. And it takes all of these things and it tries to build it. And not only does it try to build it for x86, it tries to build it for PowerPC and ARM and this, that, and the other, in a whole range of different configurations, a massive matrix of things. And that way we know, before it comes time for all of those things to be integrated, that nothing is going to at least break the compile. I mean, obviously that doesn't catch all the bugs, but it catches a bunch of people making poor assumptions or making decisions out of ignorance and having things conflict. So, brief worked example. One of the tasks, so I'm going to tell you about something that I did as a kernel developer, and hopefully through that illustrate how some of these processes come together and give you a feel for what it's actually like to be working on this full time. So probably my first big task, first or second big task, was to develop support for CAPI cards. Don't expect you to know what that means, unless you're Andrew, because he's now doing that. is extended error handling. CAPI cards are sort of peripheral. So basically, we have this card that goes in IBM systems. If it fails, we want the system to be able to recover rather than the system to just collapse in a heap. So for about 2 months, I worked on the code, right? And it was complicated, but it was conceptually a simple idea with just tricky execution. That code I then split up into a set of logical changes and sent that as a set of patches, so a set of emails, to the Linux PPC mailing list. Michael Ellerman, the subsystem maintainer, then, after people on the mailing list had looked at those patches, sorry, ignore Michael for a second. So I submitted them. People went, oh, you've missed a thing there, and you've missed a thing there. And so I had to do a few versions of them in order for them to get some consensus. Once they had got that, Michael Ellerman took them into his, and this is where we talk about release cycles a bit, into his next tree. And so his next tree is what is picked up for the next version of Linux. So at that point, it was for 4.3. So there's a 2-week window after a Linux version is released where you can send new features, and that's called the merge window. It's always 2 weeks. I don't know why. As far as I'm aware, it's completely arbitrary. Linus is the benevolent dictator for life. He gets to be arbitrary. So before the merge window opens, I need to get Michael to accept my changes. He did. Then they were in his next tree during the merge window, and he sent them to Linus, and then they became part of 4.3. But after the end of the merge window, you've got all of this new code of wildly varying quality. And so you're going to have bugs. So what happens is, at the end of the merge window, you release the first release candidate. So 4.3 RC1. And it basically, that's all the features, but now we want to fix some bugs. And so then every week for a few weeks, people send bug fixes. And so I found several bugs. Sadly, I'm not a perfect coder. So I sent my bug fixes to the mailing list. Michael picked up the bug fixes and then sends fixes to Linus to get picked up. And that's the only thing you can send during release candidate. You can only send fixes. So features go in next. Fixes go in release candidates. And then after 7 or 8 release candidates, the number of fixes gets smaller and smaller, and eventually Linus goes, looks good, and sends it out as 4.3. And then the process repeats. Another merge window opens. Any features that you'd been developing back here during RCs go into 4.4, and then the merge window for that closes, and you have 4.4 RC1, and the process repeats and repeats and repeats and repeats and repeats. So, now I'm way over here. So, hopefully you're going, that's kind of cool, and you want to know how to become a developer. So we've looked at what it's like to be a kernel developer. We've seen how Linux fits together as a project, and now we're looking at how I got there and how you might too. Kernel development is hard. Sadly, there are no two ways about this. It's a difficult problem domain. Like, the things that we're doing in the kernel are not simple. The kernel is big, at 16 million lines of code, which means it's often not clear where you would start. There are often not obvious bugs or obvious sort of places to start first. And because it's the kernel, right? So if you're a C developer, you'll go, oh, I want to print something, printf blah. I want to sort something, qsort blah. I want to search through a sorted list, bsearch blah. You don't have any of those in Linux because Linux doesn't have a C library. Linux happens before you get a C library. So any of those things that you want to do, you have to find a kernel equivalent or not do them. So fortunately, we have kernel equivalents for most of these things. And so if you want to print something, you would say print k instead of printf. If you want to allocate memory, you say kmalloc instead of malloc. But it's a whole different world. And it's hard. And ultimately, it is very difficult, I think, to get started in Linux without having a full-time work context in which to do it. The good news is, my dirty little secret is that I hadn't actually done any kernel development work before I started at IBM. So the good news is you don't have to be good at it before you start doing it. The background that I had was knowing C. That's sort of an unequivocal hard requirement. You need to know C. The kernel is written in C, and it's not getting rewritten in anything cool like Rust anytime soon. You have to learn C. You also need to be good at Git, the version control system. Fortunately, that's, you can learn that. You can learn C. All of these things are sort of achievable, just they require some work. You also need to have at least a basic grasp of how computers fit together. So the idea that you have a CPU which executes instructions which talk to memory, that you have peripherals that are connected on buses. Like, you don't need to know a huge amount about it to get started, but you do need to know something. And the biggest possible thing that you need, did I have a slide for this? No. The biggest possible thing you need is interest. That you have to, and this is how I got into it. I did electronics, I did embedded systems. I went, this area is cool. If you think this area, talking to hardware, being the layer between hardware and software, doing those sort of things where you have to know something about the real machine that you're working on, if you think that is cool, that is the biggest prerequisite, really, to becoming a kernel developer. The rest of the stuff you can learn, but we can't make you interested. So that's sort of it. We've looked at what it's like to be a kernel developer from a technical point of view. We've looked at how I got there and how you could get there. And I should probably also mention that IBM, I think, is hiring people as kernel developers. So if you really want to, you should talk to me. IBM also wants me to include a legal notice. But yeah, so that's a thing. And now we have time for questions. I don't think we have a microphone, so if you yell out your question, I will repeat it back so everyone can hear it. So the question, if I understand it correctly, is mailing lists are a bit obtuse and difficult. They often have high volume, like thousands of people posting to them, and it's not clear how to get started with them. Okay, and how do you go from messy mailing lists through to an organized project? That's a good question. I glossed over some details. As I mentioned, there are lots of mailing lists, right? So there's a general kernel mailing list, which even I don't subscribe to because it's just so noisy. The subsystems tend to have their own mailing lists, and they tend to be much nicer places to be. The other thing is that the mailing list, it's sort of the map is not the territory sort of thing. The mailing list doesn't actually define what happens. The mailing list is where we post stuff, and we hope to get feedback, but the decisions are ultimately made by the maintainer. And so the maintainer takes input from the mailing list, but there's no like voting system. It's just the maintainer makes good decisions, and that's how they become and stay a maintainer. So, yeah, to summarize, lots of mailing lists, some are nice, and mailing lists are information for the maintainer rather than authoritative sources of information. Anyone else? So the question was, was about big changes. Is that sort of big changes in, like big changes to code, or big?
For example, we start with the mailing list forever.
Big changes to process. It's a really difficult process to sort of get your head around and to get into. And this is another one of those reasons why it's, like, I don't like to say it's something that you are going to struggle to do except if you're doing it as a full-time job. But it's kind of, it's one of those, it is a barrier. It's a barrier. It's a not insubstantial barrier. And it's one of those things that is a lot easier when you're in an office full of people who already know what they're doing. Do I think it's going to change? Not anytime soon. The reason I was talking about barriers to entry was that once you get there, it works quite well. Lots of stuff gets done. And so I don't think there's any feeling in the community that we need to change. And because people need Linux more than Linux needs them, so companies will pay people to deal with all of the rubbish that Linux throws at you because they need to get something done. That's a social problem for Linux, but that's sort of the way it is at the moment.
How long does it take to go from the start of the release window all the way through to the final release candidate actually release the build?
So the question was, how long does it take to go from opening the merge window to tagging a final release? It varies. There's always a 2-week merge window and then about 7 RCs. So it's about 9 weeks. 2 plus, close enough. But it varies, right? Sometimes Linus says we need another one. So.
I think that's all we've got time for in terms of questions. So let's give Daniel a big round of applause. So just quickly to reiterate, so Daniel obviously told us a lot about what kernel hacking is and what's required. If you want to know a little bit more, I think you're hanging around for the rest of the day or the rest of the day.
I'm here until sometime tomorrow. So come and
He's
find
around.
me.
So remember, one of the key things he talked about was to be interested. So you have to be really interested in something. If you're really interested in something, then you can learn the skills. We can't make you want to learn. So I think that's a really key point. So on that note, we'll thank Daniel again with a lovely box of Lindt chocolates. I'm going to have so much fun with finding you guys and trying to eat these tonight.
Thank you very much.
Again, round of applause to Daniel. Thank you.